So good morning, and today we have three topics. First, I'll go into more detail about how to define types and functions, and then I will say more about induction, and finally I will say more about a specific aspect of the auto tactic, namely simplification. So first, type and function definitions. We already saw examples of that last time, but we didn't see the general schema. And why is that not working now? Probably because I need to, yep, this one. So let's start with type definitions, and the most important one are the data type definitions. And so this is the general schema that you see there, where you can define a data type by the name of T, and it has parameters, alpha 1 to alpha n. Those are types, component types of the data type. And then you simply list the constructors C1 to Ck, however many the data type has. And for each constructor, you give the argument types of that constructor. And, well, what does that give you? That gives you, for a start, all the constructors as functions from those argument types tau I1 to tau I ni to the overall data type that you're defining on the left-hand side. So the definition of such a data type triggers some actions in the system, and one of the actions is that all these constructor functions are defined. And they're not just defined, but useful properties are proved about them. And there are three key properties. The first one is distinctness, that two constructors are always distinct. So if you have two terms that start with different constructors, they are different terms. So for example, nil is always different from cons. Second property is injectivity, that if you have two terms that do start with the same constructor, then those two terms are equal if and only if they are argument-wise equal. So the first term is some constructor Ci applied to a list of arguments x1 to xni, and the second one is again the same constructor, but with the argument is y1 to yni, and then those two constructor terms are the same if and only if the arguments, the xi and the yi, are the same. And this is, note that the equality between the c's and the equality between the x's and the y's, that's really an equality on terms, so to speak. But this equality here is an equality on the type bool. So this is just another way of writing if and only if. And so question is, this is an if and only if. What we have there, there is a trivial and a non-trivial direction, one from from left to right and one from right to left. What's the trivial direction that always holds, no matter if the Ci are constructors or arbitrary functions? Right to left, exactly. If two terms start with the same function symbol and the arguments are the same, then the result must be the same. But left to right, it's a non-trivial property. So if the Ci is not a constructor, for example, assume the Ci where the addition function are natural numbers, then this would simply be wrong because x plus x1 plus x2 is the same as y1 plus y2 does certainly not imply that x1 is the same as y1 and x2 is the same as y2. So this is really a special property of constructor functions that's not shared in general. Constructor functions are injective. And then there's a third property that characterizes the data type, and that's induction, that an induction schema is valid for this data type. Now, I've written down the distinctness and injectivity properties, but I'm not going to write down the data type induction property because it's a long formula with lots of double indices, and it doesn't really read very well. So you can always observe it by doing induction, then you see what happens. So distinctness and injectivity are applied automatically, for example, by auto. Induction must be applied explicitly. And what does induction mean? Well, it simply means that if you have a certain property, you have to prove, if you want to prove that property by induction, it's a property of elements of that type. You have to show that the property is preserved by putting a constructor on top of arguments. That if the arguments have that property, then if you add another constructor on top, then the resulting term will still have that property. Like the successor. If you have a number n that has a certain property and you create a successor of n, it will still have that property. And this is just, in general, that works for arbitrary data types. But as I said, I'm not going to write it down. You just, if you want to do induction on a data type, you just say induction on some variable, and then you see what happens. Now, with the data type also comes a bit of syntactic sugar, namely case expressions or case constructs. So like in functional languages, if T is of a data type, then so T's type is a data type as defined in the previous slide, then you can always write case T off, and then you have such a list of patterns implying some result value T1 to Tn. And the patterns must be constructed from the data type constructors, and the terms can be arbitrary things. Now, this looks very general, and indeed you can write very complicated patterns that way, but try not to, because the more complicated your code is, the more complicated your proofs will be. So you're doing yourself a disservice if you're trying to do something very clever. Try to keep these case expressions very simple. Here's a specific syntax issue. The way the parser works, the case construct has to be enclosed in parentheses, because otherwise it's not so clear where the case construct ends. There's no ending keyword, and so that's why that's the convention that you have to put the parentheses around it. Let's briefly take a look. We go beyond lists and natural numbers to trees. And there's nothing really terribly new here, but two things I want to point out. So here we are. Okay. Yes. So here is an example of a tree definition, and it follows the schema that we saw on the slide. So here's the type name tree, and it has one argument, the elements, the contents of the nodes of the tree. And the tree can either be a leaf, which you can think of as the empty tree, or it can be a node that has three arguments, a left subtree, the element inside, the information, and the right subtree. And if you now ask, for example, what is term node, then if you consult the output window and adjust it a little bit, then you see the system correctly answers you. Node is a function that takes a tree and an A and a tree and gives you back a tree. Now, here's an example of something that will be proved automatically, that a leaf is different from a node. As I said, this is just one of the distinctness properties, and it's applied automatically. In fact, down there, it already the system already found there is a theorem somewhere in the system that matches exactly what we're trying to prove here, but it will also be applied automatically if you say apply auto. It's simple enough that it will be applied automatically. Also more complicated patterns that just consist of leaf and node, if they are distinct or the same, it will be proved automatically. Now, here's a little function definition, recursive function. Now, instead of numbers and lists, we have trees. How do we mirror a tree, of course, the empty tree is just mirrored into itself. And if you want to mirror a node with left and right subtree, you mirror the left and the right subtree, and you interchange them, and then you build a new tree. So I hope that's not too challenging for anybody here. Why have I defined this? Simply to have something interesting to prove. Not terribly interesting, but yeah, here's first an example of evaluating an expression containing mirrors and nodes. So if you mirror this tree here that has a left subtree which just contains a single node A and the right and an element in the middle B and the right subtree T, then you can already symbolically execute that. And if you ask for the value of that, you get a partially evaluated term because, of course, the system can't know what mirror of T is because T is just still a variable. But you can see the system, the evaluation has correctly swapped the two subtrees of the B node and has correctly mirrored the A subtree because it's just a single node. It becomes itself, and the mirror B is still left there unevaluated. So sometimes, if the functions are simple enough, evaluating terms with variables does work. Now, this is what we're trying to prove. We want to show that if you mirror something twice, you get back the same tree. And the details of the proof, I mean, it's clear to anybody, so it's not surprising that this proof is simple and automatic. But what I wanted to point out is what happens if you now do induction on T. So you get two sub-goals. This is what you would expect. Mirror of leaf is equal to leaf. And the second subtree is the second sub-goal is the more important one. Here you have to show it for a node rather than the leaf. And now what distinguishes this from the lists and the natural numbers is that you have two induction hypotheses. You know that if you mirror the tree T1 twice, you get T1 back, and if you mirror the tree T2 twice, you get T2 back. Those are the induction hypotheses for the subterms. And now you have to show that this will also work on the composed node of the two subtrees and some arbitrary element in the middle. So here's an example of the structural induction property that corresponds to the tree data type, and you can see you just take every constructor in the data type, and for every constructor you have to show that it has that property provided the subterms have that property. So in the node case, it has the property, a node has the property, if you mirror it twice, you get the original node back, assuming that the subtrees, the left and the right subtrees have that property. So in some sense, you can just view it as induction on the size of the tree. And because it's so simple, this will be performed automatically. Now, this is maybe a good idea to also tell you about a little display feature. Namely, you can see here the way by default these propositions with multiple assumptions are displayed is by an iterated implication. And remember, this is just the same. A implies B implies C is just the same as A and B implies C. But this is there is an alternative display facility, and that groups together the hypotheses and puts them into square brackets, and then has one arrow to the conclusion. And I actually prefer that display format, and you can change that. If you look up, let's go back to the shell window. If you look up the tutorial that is also part of the material that's in the repository, so then if you go a few pages into the tutorial, there's a footnote, and it tells you how to display things in this other format. And you have to set some plug-in options, Isabelle General, print mode brackets. Yeah, that's not something I can remember. So let's go back. Plug-in, what was it? Plug-in options, Isabelle General. Now there should be a, what was it? Print mode. Yep. Now I think you just write brackets in here and apply. Let's see if that does anything. Can we? Yeah. Maybe we have to. No. That doesn't seem to have done anything. Have I misspelled it? Pardon? Maybe that's, I should first try to restart. It's likely that it'll then work. So let's do that. So yes, now you see it has that alternative format that for me delineates the parenthesis, separates the assumptions from the conclusion more visibly in a better way. Okay, and this is automatic, so that's not the important point here. I just wanted to show you that induction can also mean you have multiple induction hypotheses for all the subterms of the recursive data type. Okay, then let's go back to the slides. Where are they? That looks like, yep. Here comes the data type that's frequently useful, the option data type. Almost seems to do nothing. What is a value of type A option? It's either the value none or it's sum, and as an argument something of type A. So you're wrapping up the elements of type A in a sum constructor, and then you're also adding a none constructor. And the point of this data type is usually to model some kind of exception or error situation that none indicates, oh, something went wrong, something didn't work out, there was no result, and sum means, yes, there is a result, and it's inside the sum. Just if you wonder what that type is, if you assume that type A has the values A1, A2, and so on, then type A option has the values, well, always none, but then some A1, some A2, and so on. And here's a typical application, just to familiarize yourself with the data type, the lookup function on a list, or on what's called on an association list. So the first argument of the lookup function is a list of pairs, and you can think of the first argument of the pair as a key, and the second argument is the value. And then you look up in this list, and you give it a key, and you get back, well, you don't necessarily get back a value, you get back a value option, because things may go wrong. So if you look up in the empty list, then you always get none, there's nothing in there. And if you look up in this situation, remember this hash sign is the cons operator on lists. So the list starts with a pair AB and then continues with some more pairs. And you look up X. What you do, of course, you have to compare X with A. And if it is equal, then you return B, or rather, you return some B. And if it's not equal, then you recurse. So that's exactly what's happened here. If A is equal to X, then some B, and else you look up in the rest of the list. So this is the typical application of the option data type. That's all I wanted to say about data types. Any last questions about that? Then let's move on to function definitions. We saw examples of function definitions. I'll now say a bit more about the features of function definitions. So first, a very simple kind of function definition, a non-recursive one, and that can be introduced just with the keyword definition, then the name of the function, its type, keyword where, and then the equation function of argument equals some term. And that can frequently be useful if you just want to, make a short function definition that stands for a larger term but isn't recursive. And there's no pattern matching here, so if you make a definition, you really have to write a function name and then just a list of variables equals to some term. So, yeah, there's nothing terribly exciting here. Now let's go. Let's move from non-recursive to recursive definitions, and then we run into a potential problem, namely you could define non-terminating functions. And why is that a problem? So what if we define a function like that? F of x equals f of x plus 1. Most programming languages allow you to do that, but Isabelle doesn't. And the reason is that if you make in the definition, a recursive definition, the system really, you and the system expect that these equations you have given to the system are really equations in the logic that you want to hold about the function. And therefore, you would expect, if you define a function like this, that you get back as a theorem that f of x is f of x plus 1. But what happens if you have that theorem? Or if you had that theorem? What could you do with that theorem? How could you get a contradiction out of a theorem like that? High school algebra. Actually, no, not high school. Sort of probably first 5 years of school.
Yeah. Why do you subtract from both sides of x and get 0 is 1?
Yes. So you can see there's a problem here. And there are two ways to solve this problem. The way that Isabelle has chosen to solve this problem is to forbid non-terminating definitions and therefore rule out this situation. There is an alternative. So that means you can define fewer functions, but your reasoning is quite simple. There's an alternative that says, well, I'm allowed to define such a function, but when I get this theorem back, f of x equals f of x plus 1, I can't just subtract f of x on both sides. I have to be more careful when I reason about subtraction, or in general when I reason about anything. I always have to check, are the things I reason about defined? And so I would then have to make a case distinction. Is f of x defined? Then I can subtract it from both sides. But if it's undefined, then the equation undefined minus undefined is 0 is just not true. So you have to make a special case. And when you use the law x minus x is 0, that isn't really a law in this more complicated logic, but it would say if x is distinct from undefined, then x minus x equals 0. So you get a more complicated logic where you always have to be prepared for undefined terms, and every deduction you make, or not every, but many deductions you make first require you to check, is this term defined or is it not defined? So you get a more complicated logic, but you get more functions that you can define in that logic. Functions that don't terminate, but then you have to explicitly reason about the possibility of non-termination or undefinedness. We go the other way around. We say, let's make things as simple as possible. There's no undefinedness, and functions must always terminate. And then our laws, for example, about numbers will become simpler because you just can forget about the assumptions. You can always, whenever you see x minus x, it's just 0. So that's the motivation for what's coming now. So all functions in HL must be total, and the system, of course, will check that. If you define a function by fun, it has the following properties. What we already saw, you're allowed to do on the left-hand side of your recursion equations pattern matching over the constructors of the data types involved. There might be more than one data type involved. And the order of equation matters. We'll see an example of that on the next slide. And then concerning termination, it's not just enough that the function terminates. The system must be able to prove termination, and the fun command insists on a particular, I mean, it has hardwired internally a particular way of trying to prove termination, namely by size measure. So to every argument, it assigns a size, and it makes sure, or it requires that the size of the recursive calls, the arguments must be smaller than the size of the original call, and therefore the function will terminate. The details are more complicated because there might be multiple arguments, and then it'll try lexicographic combinations of sizes. But basically, this is enough for an informal understanding of what's going on here. And there are alternatives if the fun command can't prove it automatically. There are ways of helping the system, but I'm not going to go into that because it's more complicated. And for what we do here, the fun command will always suffice to prove termination. And finally, very important, the system then, from your function definition, creates an induction schema that's tailor-made for that function definition. So just as you get an induction schema coming out of a data type definition, you also get one out of the function definition, and that is usually the appropriate one for proving things about that function. And we will see examples of that. So, what does this mean? Order of equation matters. Well, as I think in most functional languages, the order does matter, and the equations are tried one by one. Now, if you write a function like this is the separator function that takes an element and a list and gives it back a list and puts that separator in between all the elements of the list. Then you can write the function like this. You say, well, if there are at least two elements in the list, then you put the separator A between the first element and the rest list that you have separated with A, where the recursive call here is on the YZ list. So concerning termination, it's pretty clear that this thing terminates because the length of this list is greater than the length of this list. The system can prove that, and therefore termination is okay. But now let's look at the final line here, or the second line. Here it says, oh, for all other lists, the separation function just returns the same list. So how many other lists are there when this one doesn't match? What are the alternatives? Two. Which ones?
An empty list with one element.
Yes, empty and one element. And this is just a convenient way of writing that, writing that in with just one equation. But the system will actually internally turn this definition into a different definition because it will give you back equations that are really theorems about the function that you can work with, and it can't give you this as an equation, the second one, because that would claim that for every list. So what the system will do internally, it'll say, oh, this is just a shorthand, and really this equation stands for two equations, the two equations that you mentioned, and then in the end you get three equations out of the system, the first one and the two special cases for the second one. And so I'm just telling you this because sometimes if you use this kind of abbreviating mechanism where really one equation may stand for multiple equations, then you get back a different set of equations than the one you wrote down. You may get instances of the equations that you wrote down. In this case, you get the two instances back. Set A empty list is empty list, and set A and list with X is list with X. So that's something you have to be aware of when you make definitions where the patterns overlap. That's always the problem. If you have overlapping patterns, the system will have to instantiate the patterns, and here it will have to instantiate the X's so it no longer overlaps with the first one, and in doing so, it creates these two equations. But if your system of equations is non-overlapping, then Isabel will accept it as it is and won't manipulate it further. There is a variant of fun that's called primrec, and you can view it as a restrictive version of fun. What does it stand for? It stands for primitive recursion, and it's a particularly restricted form of recursion. And it turns out that when you program carefully, then you'll find that maybe 90% of your functions are primitive recursive. So it is quite useful. Now, I'm not suggesting you actually use it, but I'm suggesting you understand what it does, because it's a good way of thinking about recursion. You will find it frequently in, well, you find it less and less frequently these days because we get rid of the old primrec, but you can still find it in some theories. And what is the essence of primitive recursion? So here is what primitive recursion on numbers means. It means you have a function that, in this case, has just one argument that may have multiple arguments, but it does recursion over an argument of type nat, and it has exactly two recursion equations, one for 0, where there's no recursion, you just build on some base case, and you have a recursion equation for suc, where on the right-hand side you just recurse on the number that's one smaller. So that's primitive recursion for natural number. What is primitive recursion for lists? Well, here again you have a base case where you have no recursion for the empty list. G just delivers some fixed result for the empty list. And if you have a list of a cons element of an element and a rest list, then the recursion will go onto the rest list. So primitive recursion means that whatever your data type looks like, in the recursion equation, you just peel off the topmost constructor. So here the topmost constructor is suc, and there is only one constructor, and here the topmost constructor is cons. So it's always, the recursion equation is always of the form function applied to constructor, applied to list of variables, equals, and then on the right-hand side, you may recurse on the variables. But that's all you can do. So you can't sort of jump over two constructors. You peel off one constructor at a time in your recursion. And this is usual kind of programming recipe to do things like that. It doesn't always work, and we'll see things where it don't work. Typical example, Fibonacci function is not primitive recursive because you're saying what is the value of n plus 2, and you go back to n, so you go back more than 1.
Can these functions also have arbitrary arguments?
Yes, they can have arbitrary other arguments. Yeah. So just for succinctness, I've left those arguments out. Okay, so now we've seen more about the definition facilities for data types and functions. Now we want to dig more into induction, and there are some important heuristics that you should know about. And that's the contents of the next section. So the basic induction heuristic, I don't know whether I've mentioned it, I think I may have. It's a fairly obvious one that if you want to prove a theorem about a recursive function, you prove it by induction. Not necessarily. Of course, you can prove trivial theorems without induction, like f of x equals f of x doesn't require induction. But if you have any interesting property about a recursive function, it will most likely require induction. Now, that leaves the question on which argument to induct on if the function has multiple arguments. And here are the, I think I have already talked about this. If you should do induction on the ith argument of f if f is defined by recursion on the argument number I. So you always look, which is the argument that the function you induct on, which is the argument the function recurses on, and then you do induction on that argument. Now, of course, this is just a heuristic because there might be multiple occurrences of some function, or there might be multiple functions in your proposition that you want to prove, and then you don't know what is the best one to choose as the one that guides you towards the induction. But certainly, if you want to make progress in an induction, if you want to make progress in computing with a function, you have to instantiate its argument number I to various patterns, and the only way to do that is to do things by induction. So keep these two things in mind, but we'll need a bit more. And to show you what more we need, let's look at a standard example, namely a tail recursive reverse. So this is the reverse function as it is actually defined in the library for lists. So it goes from list to list, and if you reverse the empty list, you get the empty list, and if you reverse const x-axis, you reverse x's, and then you append the singleton list x at the end. Now, anybody know what the complexity of this function is? If the argument has size n? No, unfortunately not. It's n squared. Why? Because you do this append here, and the append has to run through the first list. And so if you take a very long list, and already on the first time, you have to reverse almost the whole list, and then you have to traverse the whole list again to do the append. And you will do that for smaller and smaller lists, but if you add it up, you still get a quadratic complexity. So the problem is, and that's quite a frequent situation in functional programming, if you do append and the first argument is long, then that will give you that complexity. So can we avoid this append? And yes, you can. And you can do that by a trick known as using an accumulator. And so what you get is a version that doesn't just avoid the append, but it's also tail recursive. I'll say something about that in a moment. So I call it itref, like iterative reverse, because it's more like a loop. And it now takes two lists and gives you back a third list. And the first one is the actual list that we want to reverse, and the second one is an accumulator that has the partial result in it. And if the first list has become empty, then we return this accumulator. And if the first list is non-empty yet, then we do something very simple. Then we simply shift the first element of that list that we want to reverse onto the second one, but not with an append, but with a cons. So really just a kind of shift operation, moving the first element of the first argument and make it the first, the head of the second argument. So this is not just cheap in the sense that, of course, you have to create a new const cell here, so that takes one time unit, but you don't have this reverse anymore, and you have now something that's called tail recursive, and so that means that the function call, the recursive function call, is at the outside of your right-hand side. And so that means, in the end, a compiler will be able to translate this into a loop and doesn't need stack, and will simply, as long as the first argument is non-empty, it'll take the head of the first argument and move it to the second argument. And there's no need for a stack. That's a simple loop. So this is, from a complexity perspective, a much better definition. And therefore, we would, of course, like to show that these two functions, the ref and the itref, have something to do with each other. That the itref is really a correct implementation of ref. And that's what we're trying to prove now. And we're trying to prove that if you start off with an empty accumulator and call itref, then you really get the reversal of x's. Looks straightforward. Isn't difficult either, but there's two little tricks you need to know about. So let's move to the induction demo. And yes. So this is again our function definition, and this is what we're trying to prove. That, And of course, the only thing you can do here is to do an induction on x's. There's only one variable, so we induct on that. And unfortunately, well, you get two subgoals. One x is empty, and in the other case, it's cons a x's. And if we do auto, we don't get any further. So there's we've run into a problem, and we need to look at it. And now it turns out the problem is not that we need more information, we need to prove auxiliary lemmas, but what we're trying to prove isn't quite the right property. So why is it not the right property? Well, on the left-hand side, our induction hypothesis tells us something, what happens if the accumulator is empty. Unfortunately, on the right-hand side, we see a function call of itref where the accumulator is non-empty. So we can't apply the induction hypothesis. How could that happen? We started with a theorem where the accumulator was empty. Well, yes, but if you look at what the induction hypothesis made, what the induction step is, then this is what we have to prove in the induction step. And how does the accumulator become non-empty? Well, because after the first evaluation, the first step in evaluating itref, the A is moved from the left-hand side to the right-hand side. And therefore, this is why auto leaves us with this new goal where the A has now become the only element in the accumulator, and we can no longer apply the induction hypothesis that only talks about empty lists as the accumulator. So what to do at this point? Yeah?
My question is about which induction did we use here? Is it from the function or is it from the structural induction of lists?
It's just on the structure induction on lists, and that is actually sufficient here, because if you look at the definition of itref and of ref, it is really just a primitive recursive definition. It just considers these two cases, empty list or cons. And so the induction property is not to blame. The induction is the right one. But the statement itself isn't the right one.
Maybe we set up the lemma such that the accumulator is non-empty.
Right.
The reverse function then also needs the reverse of.
Right. So this is what we will need to prove, but as QuickChat tells us, this isn't quite right, so we need to do something also on the right-hand side. So how should we modify the right-hand side? Because here... Yeah.
Y list plus reverse access.
Yeah. And auto QuickCheck found a counterexample.
Oh, it's the other way around. It's a rev axis and then y axis.
Oh, yeah.
Okay. And we don't see any more counterexamples, so it's probably right. So, but that's not enough in this course. So, induction, and now we do auto, and the base case, of course, disappears, but believe it or not, the step case still hasn't disappeared. And now, yeah, that's a bit funny. Why hasn't it disappeared? Why can't we use this equation here to rewrite the left-hand side? Well, obviously we can't, because the induction hypothesis talks about x's and y's, but here we don't have x's and y's, but we have a modified ys, because this A has become shifted onto it. Yeah?
Because we need to also induct on ys, because it would also be an empty list.
No, you don't induct on ys.
But I mean, there are multiple cases for ys.
Yes.
Taking into account.
Yes. So essentially what you're saying, we don't want to prove this for one fixed ys, but we want to prove this for all ys. Yes. And so there are two ways of doing this. You can either explicitly put that into your statement. You can write here, for example, really put in a universal quantifier and write for all ys, this one, and now you can already see the done is no longer underlined. So if you do induction and now do auto, it succeeds. And what is the difference? Well, you can't see after auto, but you can see beforehand. The difference is that now, I don't need to get up, now your induction hypothesis is stronger, because your induction hypothesis says, oh, this equation is true for any second argument, for all ys. And now you can use it in the conclusion, because in the conclusion the A will move over to here, and then you can still use this equation with a specific value for ys. So that's often, I mean, I bet almost nobody here has ever been taught something like this in an undergraduate course, and that's simply because people do this underhand. They assume that you understand that there's a difference between the induction variable, which really remains fixed. When you go from n to n plus 1, you're not allowed to instantiate the n with different values, and the other variables that appear in there, which you are allowed to instantiate with other values. And here is an example. And the universal quantifier really makes this clear, this distinction, that the other variables in your proposition behave differently. They can really be universally quantified, but your induction variable, that's the one that has to stay fixed in the step. And here we've brought this out to the front. This is something that happens all the time whenever you have a function where one of the arguments changes. Because here is a typical example. The itref function, not just the recursive argument changes, but also this other argument, the ys, changes, because here in the recursive call, the ys is no longer the one that we had. We keep changing the accumulator all the time. And therefore, in such situations where variables or arguments of functions change, you need to quantify over the variables that you put into those arguments. So that's one way of doing it. Is the principle of what's going on here, is that becoming clear? Then let me just show you some alternatives. It would be nice if we didn't have to write this quantifier there. It makes the statement itself a little bit less readable and gets in the way in other places. So there is an alternative. You can put this into the induction command and you can say to the induction, when you do induction, please quantify over some of the variables. And you can say that by adding another modifier here saying arbitrary ys. That means in the induction, the ys can have an arbitrary value, and therefore the system will implicitly quantify it. And you can see that down here, because now the induction hypothesis has this funny and symbol, which is really a different kind of quantifier, a different kind of universal quantifier. It's again a universal quantifier, but not the one from H to L, but the one that is built into the Isabelle framework already. And logically, there is no difference. You can convert between the two, but operationally, the system prefers this quantifier. It can deal, in some places, it can deal more gracefully with this quantifier, and therefore, if you put an arbitrary here, it will use the other quantifier. Don't worry about it. It's logically the same. It's the same thing as if you put a universal quantifier there by hand. It's just the system does it in a way so that it's most convenient for itself. But you can read it as a universal quantifier. For all ys, this is equal to this. And that's simply a kind of a inheritance from the fact that Isabelle is a two-level system where you have a minimal framework logic that has things like these implication arrows and this quantifier in order to start the framework, to set up logics, and then inside that you set up the actual logic that you're interested in, which has its own quantifier and implication arrow. So this is, you can say, an artifact of the architecture, so don't let it worry you. And this is really the way I recommend to do these inductions. If you recognize that one of your variables needs to be generalized, then you put this arbitrary there, and then you get a more powerful induction hypothesis where this variable is already universally quantified and other arbitrary values can be put in for the universal quantifier. That's why it's called arbitrary. And this is really all I wanted to say about induction heuristics. So let's get back to the slides and let's summarize this. So, two important things, both in a way come under the heading of generalization. The first one was the more tricky one. Typically, if you're proving some statement that has constants in it, like the empty list, there's a good chance you will need to generalize this statement. And the simplistic motto here is replace the constants by variables, but of course it's simplistic because that's not enough. You then have to modify the statement to take the variable into account. Remember, if we go back, we had to modify the statement not just by making the empty list here into a variable, but also by figuring out what to do on the right-hand side and to write and make the right-hand side look like that. And now actually you get a much better understanding of what this function itref does. It takes the first argument, turns it around, and puts it in front of the second argument. And the fact that if the second argument is empty, that this is just reverse, is a special case. In fact, you can prove that special case if you say, well, I originally wanted to prove something more special here. Now I see this general thing. How about the special one? Let's give this a name. Call it itref ref, for example. And for simplicity, we just make it a simp rule. And then if you now want to prove lemma itref x's empty list is ref of x's, now you don't need induction. Now it's quite sufficient. This equation, of course, will prove this because you can apply this equation and it rewrites it into ref of x's append empty list, and append empty list goes away by another simplification step. So if you say by auto, this will just vanish, and you get the special case that you originally wanted. So here's an example of something where you don't need induction because you have already proved a much more general property by induction, and this is a trivial consequence of it. So this is the first thing you may have to do. The second form of generalization is that you generalize over the other free variables, the non-induction variables, and the standard way is to use this arbitrary phrase in the induction command. Okay, now so far all the proofs were by structural induction on the data types involved. Structural induction always means you have a term that is of the form constructor applied to some variables, and you can assume that the property holds for the variables, and then you have to show it for the constructor term. This is a very special induction schema, and it's an induction schema that corresponds to primitive recursion. But not all function definitions are primitive recursive. So, yeah, that's what I just said. So the induction step means in each induction step, one constructor is added, and you have to show that the property is preserved. And in the recursion call, in a primitive recursive function, one constructor is removed, and you recurse down to the argument of that constructor. So these two things fit together well. If, on the other hand, your function has a more complicated recursion pattern, then structural induction is likely not to help you anymore. And so, therefore, we need induction properties, induction schemas, for more complex recursion patterns, and luckily, the induction schemas will come right out of the function definition. So you don't have to do anything, you just have to apply them. And here's an example of something that's called computation induction. And why is it called computation induction? Because it follows the course of the computation of a function. In this case, it follows the course of the computation of the diff2 function. So diff2 on natural numbers can be defined, so division by 2 can be defined by 3 equations. On 0 it's 0, on 1 it's also 1, and on suc of n it's diff2 of n. So you actually peel off 2 constructors, and then you put the successor outside. So that's a recursive definition of division by 2 on natural numbers. Now, this is clearly not primitive recursive, and if you try to prove something about this property, about this function by structural induction, it'll work, but it'll be ugly. Because you can't directly apply this equation because the induction will only give you one successor, and then you have to do another case distinction, and sometimes it won't work at all with more complicated functions. So structural induction is not the way to go if you prove properties of this function, and you should use the induction property that comes directly out of the function definition and looks like this. It's called always function name dot induct, is a theorem in the logic and a theorem that represents an induction schema. And this is what the induction schema looks like for this particular function. So it says if you want to prove P for all m, then what you have to prove that it's true for 0, you have to prove that it's true for successor of 0, those are the two base cases. And you have to prove that if it's true of n, it's also true of successor of n. That corresponds to the recursive call, where you go down from suc of n to n, and in the induction you have to go up. You have to show that if your property is true of n, it's also true of suc of n. So note that this induction schema does not mention the function diff2 at all. It's just a schema that tells you a specific schema of how to prove things about natural numbers, that tells you it's okay to prove things about natural numbers if you can prove two base cases, 0 and 1, and if you can prove that from n you can go to suc of n. So this schema will basically work nicely for any function that follows a similar recursion pattern, but it doesn't have to be the diff2 function. So this induction schema that the system proved for you is just a summary of the termination argument, essentially. The system could prove that this function terminated. Why? Because this is you can't go on forever peening of two successors. Eventually you'll hit either 0 or 1. And the system could prove that, and therefore it could generate this induction schema out of it. And in truth, I left this out. This induction step, of course, has to be proved for one fixed n. So that's, again, the situation where you fix the induction variable, and that has to stay fixed over this implication here. So, just to be clear, this quantifier binds not very strongly, so that means the n here, the quantifier goes all the way to here. It's not that you're universally quantifying the assumption and then prove something from it. You're universally quantifying the whole thing here. So this is different from what we did previously when we generalized. There we just universally quantified the induction hypothesis. That was different. And there we quantified over some other variable, but here we are quantifying over the induction variable. And here we're just saying, oh, in this implication, please consider one fixed n. Now, yeah, this is what computation induction in general gives you. If you have a function for simplicity of just one argument, then the system will provide this induction schema function name.induct. And what we have to prove in order to prove p of x for all x of that argument type here, you have to prove, basically, you look at each defining equation of the function. They all look like that, where here you have some pattern on the left-hand side, and here you have recursive calls R1 to Rk, and then you have to go in the induction in the other direction. You have to prove the left-hand side, the E, that the property holds for E, and you have to assume that, you can assume that the property holds already for the arguments R1 to Rk. And that's simply why are we allowed to do that, because the system has proved that these R1 to Rk are smaller in some sense, because that's exactly what the induction, the termination proof relied on. The system could find some ordering so that the arguments of the recursive calls are smaller, and therefore we are now allowed to use this as an induction proof, because we are only assuming that p holds for smaller values, and then we have to prove it for a larger value. So this is the principle that is manifest in computation induction. And you should really, that's something you should understand. Of course, you can just blindly apply it, but then you may not understand what you're getting. So it's really the idea is always you assume the property for the arguments of the recursive calls, and you have to prove the property for the argument on the left-hand side. So basically, that the property propagates up in the recursion tree. If you think of the function calls as a recursion tree, then you show that you can prove the property by propagating up the recursion tree until you've shown that it's really true at the top of your initial call. Yes, and this is the motto here. The induction follows the course of the terminating computation, going from bigger values to smaller values, and in the induction, of course, you go from the smaller values to the bigger values. Yeah. And if you have a non-primitive recursive function definition, then it is best to prove properties by f with f induct. Properties about f with f induct. So how do we apply that? We'll see it in examples. Here's just the general slide. So if you have a function f now of arbitrarily many arguments, and this is the form that you would apply the schema f induct. So you say induction, but then you augment your induction command and say to the system, please use the rule f induct in your induction, and please do the induction over some terms a1 to an. Now, where do those come from, a1 to an? Heuristic is that there should be in your proposition that you're trying to prove, there should be some call of the form f of a1 to an. And then you just take these arguments, give them to the induction command, and say, please use the induction schema associated with f. And ideally, the AI should also be variables. Otherwise, it won't work so well. But all of these are just heuristics. But this is not just a heuristic, this is a schema. So this is how you write it down. It's just a question, where does the a1 to an come from? And in most cases, you just look at your proposition, and there you spot some call of f, and then you just take the arguments, and you take the arguments where, if there are multiple calls, please choose the arguments where these are all variables. And we can now see how this plays out in a concrete example. This is again our separator function, and now I have taken I've defined it by making the two base cases explicit and not by hiding them in this second rule that says sep of a axis is axis. Here I really write down the two base cases, and then comes the recursion case. And now I want to prove something about this function. And you can see, again, it's not primitive recursive. There isn't one case for nil. There are two base cases, and in the recursion, in the recursive case, you look at two constructors rather than just a single constructor. So you could prove this by structure induction, but it would be very ugly. So what you do is instead, like this. This is what we're trying to prove, this property here. What does it say? On the left-hand side, you first separate the elements in X's by A, and then you map F over it. And the claim is that is the same as if you were to first map F over X's and then separate the elements of F, well, not by A now, but by F of A. I hope you can see this commutation property in your head, that this is actually a property of the function sep, or rather the interaction between the function sep and the map function that applies F to all the elements in the argument list. And now we're following the recipe on the slide. This is a property. a property of function f, a function sep, and so we should prove it by the induction schema associated with sep, and therefore we write induction and add this modifier rule sep induct. And also now, what do we want to induct on? Well, here we say a and x's, and why is that? Because here we have a call of sep that has exactly a and x's as arguments, and those are variables. You could also say, here's a call of sep, but now it has these big terms as arguments, and if you try to give them to the induction, things will go wrong. It's always best to just induct on variables. And so this is what you're doing here. You're doing induction on a and x's, and you're following the sep induct theorem. And if you look at it, you can always say, what is sep induct? And here you see the induction schema, and it's not very readable because everything is, not everything, but the P is prefixed with a question mark, but you can kind of see here we have the base case, which corresponds to this base case here with A and the empty list. Oops. Here we have another base case, P of A and the singleton list X, and here we have the induction step where again, P is applied to the same arguments as we have on the left-hand side of the third line of sep, and we assume that P holds already for the recursive arguments, the Y, Z, S, and A. So this induction schema really corresponds one-to-one to the recursion equation.
But in third induction proposition, there is no X on the left side.
Sorry, where?
In the third position.
You mean in the induction schema down here?
Yeah, in the third position. Yeah, there is no X there.
What do you mean no X? Here. This one? Yes, indeed. There isn't, because it comes from the right-hand side of the recursion. So this is what you're allowed to assume. You're allowed to assume that P holds for the arguments of the recursive call. So you assume that P holds for Y, Z, S, and you have to prove that P holds for the arguments on the left-hand side. And here we have the X on the left-hand side.
So the X...
it's difficult to see it in both, yeah.
The constructor where X is added to A is missed on the left-hand side. Because it's not part of the proposition.
What is not part of the proposition?
In the third definition for set, we have X hash A hash step of A.
Yes.
And here in the induction hypothesis, the third one, we don't have X hash A.
Ah, right. No, indeed. The induction schema is always only relating the recursive calls to the original call. The thing that's around it is of no consequence. So if you go back to the slide, let's look at this schema. This is the schema, and it says you have some equation, and around the recursive calls there can be other stuff. But the induction will only focus on the arguments of the recursive calls. We can assume those, the proposition holds for those, and then we have to prove it for the argument of the original call. So now neither the function f nor the context on the right-hand side appears in it, but really just the arguments of the calls of f. And that's because those arguments are supposed to get smaller. That's what gets smaller, and therefore that's what you can use as an inductive stepping stone. But yes, please do ask these questions, because otherwise I'll just go too fast and it's easy to miss things. And if we now go back to our original goal and we apply our induction, how many subgoals do we expect? Well, of course, 3. 2 base cases where the X's has been replaced by empty list and singleton list, and 1 proper induction step. And that's more or less what we see here. So here we have the number 1 is the first line, it corresponds to the first equation for SEP, number 2 to the second equation for SEP, and now number 3, it becomes a bit hard to read because there's so many maps and seps and conses there. But you can still see this is the assumption, which is exactly the equation that we're trying to prove, but with x's replaced now by this pattern yz's. And here is the conclusion, and here x's has been replaced by x, y, z's. So, and from a size argument, this makes perfect sense. We're going from a smaller list to a bigger list. We've added one more. And that's exactly what the sep function does. It goes from a bigger list to a smaller list by removing one element. So, and the nice thing is, because the proposition is so simple, auto will just prove it. If you try to do structural induction here, it becomes a mess. So this is an important heuristic that you should follow. If you have more complicated function definitions, use those induction schemas that come from the function.
And do you also have a heuristic about which functions we need to use to index?
No, that's more complicated. Yes, indeed. So that's a good question. You could perfectly well argue that why don't we do an induction on x's, because here we have a call with map and x's, and map is defined by recursion on x's. So that would be a perfectly valid way of trying it, but then you find you don't make progress, and therefore at that point you say, oh, maybe I should try something else. Yeah. And another kind of heuristic is that sep is the I don't have a clear heuristic to tell you why we should induct on the sep arguments rather than the map. Yeah. So those were the two important things I wanted to tell you about induction. One is this generalization business, including this quite system-specific generalization with quantifiers via arbitrary, and the second one, this computation induction idea, which we will use a lot because not all the functions will be primitive recursive. Yes, we had that. And so I want to conclude today with saying a few words about the workhorse that's used under the hood of the auto tactic, and that's simplification. I have already sort of hinted at it, but I haven't stated anything very precisely, and now I'll do that. So what is simplification? Simplification simply means that you use an equation exclusively from left to right. And the fact that this really gets simple, that's what you hope. Of course, it may not get simpler by using the equation from left to right, but it's a terminology that's being established. And you do that as long as possible, and that, of course, is in red, because as long as possible may mean if you have chosen the wrong equations, then it goes on forever. So there is a termination problem here, but it's not termination of a function definition, but it's a termination of some proof procedure. And that is something that you can't always guarantee. So I will frequently talk about a simplification rule, but that's just it's the same thing as an equation, but the word simplification rule emphasizes that it's used in one direction only. And there's another term here. Term rewriting or just rewriting is again a synonym for simplification. So I'll be switching between those terms all the time. And here's a simple example. If we are given these four equations here, the first two we are already familiar with. They define the addition function on natural numbers by recursion over the first argument and pulling the successor out of the first argument. And the other two equations, they are an incomplete definition of less than or equal on natural numbers. So if you try to compare two natural numbers with less than or equal and both are successors, well, that's the same as comparing m less or equal n. So note this equation, this equality is an equality of type Boole between formulas. And 0 is less or equal any term, so that you can really rewrite to true. And here's an example of how these rules are applied. So let's assume this is the proposition we're trying to prove, and we say by auto, or apply auto, then auto will go away and try and use these equations, and might use them in the following order. So I'll use them by accident, by coincidence, in exactly the order that they're listed here, but that's really just a coincidence. So you can use equation 1. Why? Because there's this subterm here, 0 plus something, and so equation 1 will say, oh, by equation 1, this comparison is the same as this comparison where we have replaced 0 plus suc of 0 just by suc of 0. Then we can use equation 2. Why? Because on the left-hand side, we have a suc of something plus something else, and so the successor gets pulled outside by equation 2. Now we can use equation 3 on the top of the whole proposition here, because here's a successor and here's a successor, so we can peel off the successor. Is this the only possible? At this point, could we have done something else rather than use equation 3?
Yeah, 0 plus x, successor from 0 plus x is a successor from x.
Yeah, so we can apply down here, we can apply this equation and replace 0 plus x by x. We could do that, but we haven't done that. But it's perfectly, that also makes this kind of proof search non-deterministic, and if you are unlucky, then the auto proof method will choose the wrong path in quotes, and you can't prove it. Although if it had taken a different path, it could have proved it. So these things are just heuristic procedures. And now at this point, of course, you could still apply 0 plus x and contract that to just x. But you can also immediately apply equation number 4 and replace that whole proposition by true. So this is how the simplifier works. And it's important to understand that it doesn't just work at the top of the term, but it can do simplifications anywhere in the middle of the term. So this is what I mean by rewriting. There's a variant or a complication of this that's called conditional rewriting. So your equations can also have assumptions. So in this bracket notation, it would look like this. So you have an equation, left-hand side equals right-hand side, under k assumptions p1 to pk. And how does the simplifier treat this? Well, it'll only use this implication provided it can prove the premises. So such an implication is only provable, only applicable if the premises are provable for that particular instance where you try to apply it. And here's an example. We have two equations here. First one, unconditionally, p of 0 is true. And the second one is conditionally, if p of x, then f of x equals g of x. And now let's see what happens if we try to simplify f of 0, and then I claim f of 0 can be simplified to g of 0. Why? Because you can use this conditional equation, because if you try to use it on this term f of 0, you have to prove p of 0, and you can prove p of 0 because the first equation will simplify p of 0 to true. So that's why the second equation becomes applicable. On the other hand, if you try to simplify f of 1, if you try to simplify f of 1, then it'll just stay unsimplified, because it'll try to use this conditional equation, and then it'll say, oh, I now have to prove p of 1, but with those two equations you can't prove p of 1, and therefore f of 1 is left alone and is not changed. So you have to understand this when you state these conditional rewrite rules, that it actually recursively invokes the simplifier. So it'll say in this case here, if you have this conditional equation, it'll say, okay, we try to rewrite f of 1 to g of 1. Now let's first prove f of 1, p of 1. And then it'll recursively go away and try and simplify p of 1 down to true. And you can see that there's a danger of non-termination here. This might become more and more complicated. So you have to be aware conditional equations are a source of non-termination if you don't, if you use them carelessly or without paying much attention. Now, of course, you can always experimentally use things, and then if the system disappears into a purple hole, that is one of those proof commands becomes purple, then you know it's not simply it's not terminating, and you've done something. You've screwed the system of rewrite rules up. So yes, termination, simplification may not terminate for various reasons. Isabelle really only uses those rules blindly, and it does not check at runtime if things go wrong. It'll just say, well, that's your problem. You have to then remove the command if it becomes purple and you see it doesn't terminate. Here's a typical example. If you give it these two equations, then it'll just go on using them forever. So don't do that. Now, it's a bit more complicated if you have a conditional equation, but there's still a good heuristic here. When should you allow such a conditional equation as a rewrite rule? Well, the first one is, of course, in any rewrite rule, the left-hand side should be bigger than the right-hand side. Something should become simpler when you go from left to right. Otherwise, of course, things can blow up. What your measure of simplicity is, that's more complicated. It's not necessarily the syntactic size. Terms may go bigger in syntactic size, for example, by a distributivity rule, but you can't go on applying distributivity forever. Eventually, everything will be multiplied out. So, in principle, that's not a bad rule, although it may make the term grow. But so saying what has to become simpler, or in what sense L is bigger than R, that depends on your particular application. But not just bigger than R, but also bigger than the PI. Why? Because when you try to apply this rule, you're in a situation where you have a term L that you're trying to simplify. And you want to simplify to something smaller, that makes sense. But also, in the recursive invocation of the simplifier, when you try to prove the premises, it had better not be a more difficult task, because then you could potentially generate more and more difficult tasks by moving from the left-hand side to the premises. So ideally, the left-hand side should be bigger than everything else, both the right-hand side and all the premises. And here, just as a simple test, look at these two equations and see if, by just some simplistic criteria, which of those two conditional equations fulfill this blue criterion and which one doesn't. One of them fulfills the criterion and one of them doesn't. Yeah.
The lower one does.
Pardon?
The lower one does.
Why?
Because it reduces the successive function to n.
So you're claiming in the lower one, this term here is bigger than this term? That's what it should have. The left-hand side should be bigger than everything else. So are you saying this is bigger than this?
Oh, maybe I got it.
Yes. Maybe you got it fit. Maybe this one here, this left-hand side is bigger, well, certainly than the right-hand side, but it's also bigger than the premise. And yes, this one is okay, this one is a no-no. In fact, if you try to use this, you will immediately get into a non-terminating loop, because if you have some term n less than some other term n, it'll say, okay, let's try and rewrite this to true, but first we have to prove that successor of n is less than n. Then we can use the same rule again, and then we start stacking up successors in the first argument. Whereas this one is nice because we remove a successor when we go from here to the premise, the premise becomes simpler. So, but you can always just do things naively and then backtrack at the point where things don't terminate. Although I don't recommend doing that, because at the point where things don't terminate, it can be tricky to find out what the source of the problem is. So think about it first when you make something a simplification rule. Think about those criteria. So what does the proof method? There's a proof method called simp, and that's a core of auto. And what does it do? If this is your proof state, So you have some assumptions, P1 to Pm, and you want to prove C, and you now apply simp, the proof method simp, and you say, please add the equations 1 to n, which you have proved further up in your development. Then the following happens. It will simplify the whole proof state, so both the assumptions P1 to Pn and the conclusion C. And what will it use? It'll use all the lemmas further up that have the simp attribute, and not just in your own theory, of course, everything that you inherit from the theory that you base yourself on. It'll use all the rules from fun and data type. Of course, from fun you get the equations of the function themselves. Those are used. And from the data type you get these distinctness rules that different constructors are different, and that injectivity holds. So there's also some helpful stuff coming out of data type. And of course it will also use all these equations 1 to n as rewrite rules. And it will additionally use the assumptions P1 to Pm to simplify each other and to simplify the conclusion. So it'll try to basically do as much simplification as possible. And you can, there are variations on this simp. Instead of adding something to simp, you can also delete something. That means you remove locally a simplification lemma. Much of the time, if you locally remove a simplification lemma, that tends to show maybe you shouldn't have added it in the first place. But sometimes you have simplification lemmas that work out fine in 98% of the cases, and in 1% of the cases they just do the wrong thing, and that in those 1 or 2% you remove them. And of course you don't have to add or delete something, you can also just call simp without any arguments. And auto is similar to simp, but auto acts on all sub-goals. Simp only acts on the first sub-goal. So simp is more focused, and it doesn't. If you call auto and you have 5 sub-goals and afterwards you have 3, it's very difficult to figure out which one was which, because it might have solved sub-goal 2, 3, and 4, and it might have blown up sub-goal 5 into 2 sub-goals. So if you get to that situation, it's time to use just simp, because it'll let you focus on particular sub-goals. And auto is more powerful than just simp. It does other things that we'll get onto later on. And auto can also be modified. And then it looks like this. Now, why doesn't it just look like auto add and auto del? Why does it say auto simp add and auto simp del? Because with simp, there's only one thing you can modify, namely the equations that it uses. With auto, there are many things you can modify, and I'm just telling you about one thing. And here you're saying, this is the command, and now you say, oh, and please, in the simplifier part of auto, add this, and in the simplifier part of auto, delete this. So this is the command, and these are the modifiers. And you could also, And similarly here, where you say simp, simp is the command, add is the modifier. Yes, this might be helpful. If you make a definition, it is not used automatically by the simplifier, and that's intentionally, because definitions are sort of, you add a new name, and that is like a barrier. You don't always want to expand this name. You want to create sort of a new level of abstraction. And that's why it's not removed automatically, but you can remove it if you want to. Then you say sim and add fdef. So that's if your function is called f, then if you want to expand the function definition and it's defined in a definition, then you use this schema here. So yeah, f is the function whose definition is to be unfolded or rewritten with or whatever. And finally, this can be very helpful if you have case constructs or if-then-elses in your definitions or your functions. So this is what both simp and auto will do automatically. You don't have to do anything there. If you have a big proposition, so this is just some informal notation, so you have a big proposition P, and inside you have an if-then-else. If A, then S, else T. then SIMP will eventually split this up into two cases. It will say, oh, this proposition here is equivalent to these two propositions, or to the conjunction of these propositions. One where I assume A, and then I have to prove P of S, the then part, and one where I assume not A, and then I have to prove P of T, the else part. So that is, if either your functions or your proposition that you try to prove contain if-then-elses, then those if-then-elses will get split up into different cases. And if you're lucky, the simplifier can then solve both cases, or at least one case automatically, and you're left with a much simpler situation. On the other hand, if you're unlucky and you have many if-then-elses and they all get expanded, you can see what happens. With each expansion, the proposition becomes bigger and bigger. So that can also lead to situations that are unreadable, and then you basically have to figure out what additional properties you need in order to make this nest of implications go away. So I'm just telling you this. If you have many if-then-elses, you might run into difficulties with these proofs. So always try to keep the logic in your program as simple as possible so that you don't run into huge case explosions. But in many cases, this is really very beneficial. So this happens automatically. What does not happen automatically, if you have a case construct over any data type, they are not expanded automatically because that is a source of potential non-termination. This just blows the term up, but it's going to terminate. Eventually, everything has disappeared. But this might non-terminate if you interact with some function definition. So here's an example. If you have a case construct over natural numbers, case E of 0, then A. If successor of 0, then a successor of n, then B. You can explicitly perform a case distinction here, and it'll give you two cases. One, okay, let's assume this expression here is 0, then we have to prove P of A, because that's the return value in the 0 case. And here, for all n, we have to show if E is suc of n, that's the second case, then P of B. So P is the enclosing context. And so we now, in the enclosing context, the whole case expression has been collapsed down to B, because we're assuming that our expression E that we're making the case distinction on is a successor expression. And in order to do that, you can modify the simp method, and you can say simp, and please split all case constructs over natural numbers. So this is the particular pattern that you have, the magic incantation that you need to do, and it says, that's the proof command, that's the modifier, the split, and here it says, oh, and please split all the cases over natural numbers. So you can't say this one or that one, you just will split all the ones with natural numbers. And in general, you can do this also with auto, and in general, it'll be in the name of the type over which the case construct ranges, and then dot split. So like t.induct, we also have t.split, and that focuses on case constructs of a particular type. And yes, this is how this is really the last slide. There's a special case construct, namely for pairs. So far, we've avoided pairs because they can sometimes lead to complications. So if you have some context P, and inside you have a let expression, let, and now here comes a pair pattern. Let xy equal to t in, and here comes some term u, which uses x and y. Then you can expand this, and somehow, yeah, because this t might not be really a manifest pair. It might not be pair AB, but it might be a function call that eventually will return a pair. Now what you can do is you can get rid of this let, and similarly can get rid of this case. These two expressions are actually the same. This one here, this let, and this case is just another way of writing the same let here. Case T, you analyze the T. If it's a pair that contains x and y, then you return u, and x and y, of course, being substituted by the two components of T. And those are the same. That's just, yeah, in any functional programming language, they will be the same. And how can we split that up? You can split it up into this form, where you now explicitly assume, okay, let's assume T is a pair, and then we prove P of this U term, the result of the term. And this is done with a specific calling convention. So if you see in your proof state something like this and something like this, there's a good chance that you might want to split this up and use this particular magic incantation. So don't learn these things by heart. Just remember that they're there, that splitting something with pairs that has a let or a case with pairs in it requires this special command. And why is it called prod.split? Because the pairs are called prod inside. So the prod is the type constructor that takes two arguments and produces the pair. And is, of course, displayed as the Cartesian product. Right, thank you for having stayed on for another 5 minutes. I will not give you the demo now. I'll give you the demo next time. In fact, you may not need it anymore because you'll have the tutorial today and there'll be demos about that anyway. But I'll come back to it. Okay, thanks again and see you next Friday.